So I guess I'll just make a start then. I don't know if any of you, I don't think any of you were, but if you were at this Morzine summer school run by Nick and Chris a few years ago, this is a similar talk to what I had there. But none of you were there, right? All right, then you're good. So I'm going to be discussing the roles of principles in our search for quantum gravity. And the first part of this talk will be about the holographic principle and the entropy bound. And then the second part will be on singularity resolution. So, okay. As a bit of a recap from yesterday, what is this problem of quantum gravity? Well, we're looking for a theory, and it's not being primarily motivated by empirical concerns. So we don't have these observed anomalies that are thought to necessitate the search for this new theory. We don't have a theory, and it seems like we don't know what the theory should be like or what it's even supposed to do. Instead, we've got this plurality of approaches that are doing different things, adopting different criteria of success, and then trying to understand what quantum gravity is, means looking at whatever principles and criteria that it's supposed to define it. So I had this idea of looking at the motivations and constraints that we're expecting the theory to satisfy, and then frame them as principles, and then try to assess these principles. So I think principles, quite interesting in physics, right? Especially in times of crisis. So it's always when hit a bit of a roadblock or a bit of a fork in the road, we don't know what to do, that we turn back to evaluate our principles and maybe to look for new principles. So let's now get in our time machines and take a trip to the 1904 World's Fair in St. Louis. And this was supposed to just be one slide, but then I got fully obsessed the more I learned about it. So we're really going on a trip now. Off we go. So here is the giant wheel. Here is a blimp, wonders of aviation here. Here is an elephant made entirely of almonds from some exotic land. Here are the first ice cream cones. Apparently it was also the first cotton candy, or fairy floss. What do you call this in Italian? Frizzicciato? Okay. You can find it here. And they had these wondrous exhibits. So this is like a reconstruction of the Tyrolean Alps. This exhibit alone was 19 acres. And the mountain was 100 feet high. I'm not sure what that is in SI units. Does anyone know what's 100 feet? 31 meters, there you go. And right next to it was a reconstruction of Blarney Castle in Ireland. We also had Chinese palaces, lots and lots of stuff going on here. We also have, as you can see here, a reenactment of the Anglo-Boer War. It doesn't say how many meters that was. We had the first Olympic Games, apart from the original Olympic Games, presumably. Have a read of that link, because that shit was crazy what went on in these Olympic Games. We've got all sorts of new technology. It's really, really exciting. You've got the first medical X-rays here, the first infant incubators. We've also got these marvels of thermodynamics here, of course, giant turbines, 3,000 horsepower. And this palace of electricity, showing how, electricity is going to revolutionize our life, new applications for electricity. And you can see the crowds here. So it was really, really busy. It went on for 7 months, apparently. It also had some less cool things like human zoos. And apparently some of these were part of the Olympic Games as well. So yeah, you're getting the idea here. There's a lot going on. It's really, really exciting. And please, if you ever, one of you guys is going to make a time machine, I know you will. When you do, take me back here. So yeah, this is the French Salon. Yeah, I should have put up pictures of the Italian exhibit. We'll have a look over drinks after, right? The first private automobiles that you can buy for yourself as well. All right, so what are we doing here, of course? Of course, we're here for a great scientific meeting. Because here we have lectures by Boltzmann and Poincaré. So, of course, these two speakers were invited to discuss the connection between natural philosophy and applied mathematics under the normative science division of the International Congress of Art and Science. So let's start with Poincaré's lecture. So here we're looking at, this, yeah, like I was saying, I find this whole era so exciting. It's like you're on the cusp. Everything new is happening, all these great new technologies, new discoveries, and you're really looking towards the future of physics. It's very, very exciting. But he's saying two crises. One has already passed. This was the crisis where we realized that Newtonian-style laws, being mechanical force laws, were not capturing the full range of observable phenomena. And from this crisis led to physics of the principles, he says. So what was done? Abandoned was the thought of exploring the details of the universe, of isolating the parts of this vast mechanism, of analyzing one by one the forces that set them going. We're not getting this kind of physics of micro details or mechanics anymore. Rather, we look to certain general principles that have precisely the object of relieving us of this minute study. We're no longer looking for these little goings on. So we're giving up studying objects, forces, and mechanisms, and instead we're moving to look at some general principles without needing knowledge of the details going on. So he then goes on to identify some of the key principles that he sees as important here. First one being the principle of the conservation of energy, Carnot's principle, so the second law of thermodynamics, Newton's principle, quality of action reaction, I guess that's Newton's first or third. Principle of relativity, being that the laws of physical phenomena must be the same for stationary observer as for one in uniform motion, conservation of mass, principle of least action. So these are the ones that were identified following this crisis with Newtonian physics and led to, of course, Maxwell electromagnetism and this revolution in how we're thinking about physics. So this is held up as the supreme example of such physics of principles. And now, after this first crisis, he says we found ourselves in the midst of the second crisis. The problem is, each of these principles, these beautiful principles that have arisen out from this study, it seems like they're all under threat. He goes through different examples of how each one is being challenged by the new discoveries. In particular, they're coming from empirical observations. These threats are coming from Brownian motion, radioactivity, Michelson-Morley experiment, and experiments accelerating electrons. Curiously, as you can see, he's not mentioning black body or photoelectric effect, which would have been kind of known these days. He's thinking of them as more like, well, it must be a glitch, These are very new observations. Let's treat them a bit skeptically, but I think that's interesting where he doesn't mention those. So people loved this, great applause, everyone's on board. And of course, what happens the very next year, Poincaré gets proved right, thanks to Einstein's Annus Mirabilis, where he publishes these 4 papers, showing these principles coming out. And of course, in this, I think it's a newspaper article, maybe some people have seen this, he publishes this short article in 1919, essentially saying similar thing to what Poincaré said about the physics of the principles. He's saying we can distinguish between constructive theories or kind of constitutive theories, right? Where we want to build up our descriptions of complex phenomena by appeal to smaller mechanisms and smaller things going on, basic results, the constituents, and then you get back up to the phenomena you want to explain. He presents those as kind of the goal of physics. This is what we want. We want some sort of micro explanations. But just as Poincaré said, when we're being challenged and we're not able to come up with these micro explanations, we turn to the principles. So then we're building these new theories by appeal to more general principles. And these get elevated from the empirical observations, and we then kind of need to go back and help use those principles to help us get a constitutive theory, which is still, at the end of the day, the goal. Okay, so I think it's a bit natural to ask now. Richard has been saying this, we're in a bit of a crisis. Does quantum gravity represent a third crisis? You know, following from that first one, from Maxwellian physics, Newtonian physics, the second one, Maxwellian physics. And then it seems now perhaps we're in a third crisis. We've got these beautiful principles that have arisen from Einstein's discovery of quantum mechanics and special and general relativity. And now they've come under threat, not from observations, but from conflicts with each other, right? So the principles themselves that arose out from this discovery are what's causing us problems. So the suggestion, do we need a new principle theory? And Smolin is one who's argued for a principle-based approach, but most approaches to QG arguably can be seen like attempting to build up space-time from more micro-constituents. So I think also we should recognize, as we mentioned yesterday, this third pillar of modern physics. What about thermodynamics? This must have principles as well that we can appeal to and they become important now. Maybe these can help solve the crisis of the conflict between principles of these other two frameworks. So talked about Poincaré, talked about Einstein. What did Boltzmann say at our meeting here? Let's go to his lecture. And it's hard to find his lecture because no one's written on it, no one turned up. They didn't even want to put him in the physics category. They put him in the mathematics meeting. And he reluctantly titled his talk, "The Relations of Applied Mathematics." Why? He was pissed off because he actually got up there and said this, look, I'm not a mathematician. I shouldn't be here in your mathematics category. I'm a physicist too, though you don't seem to believe me. He actually says, one day theoretical physics will be legitimately recognized as a field of physics. But at this time, yeah, the physicists didn't like it at all. They're being enamored by Maxwell's theory. That, as I said, they're taking this as the pinnacle of modern physics and enamored by it replacing this mechanical worldview. Otherwise, they're favoring more phenomenological approach using few general principles, so they liked these kinds of approaches. Boltzmann is up there with his new theory that's a constituent theory. Hey, we can go back and explain thermodynamics in terms of little things using kind of Newtonian mechanical forces. So of course they don't like this. They think it's total like speculation. What evidence do we have for these atoms you're talking about? So he's trying to defend this view. And this is it in 10 points, I think. First, science needs bold hypotheses. Two, the atomic theory is a bold hypothesis. Even continuum theories, which we use, they have bolder hypotheses. The atomic theory helps us understand more than these energetic, phenomenological, and other continuum theories. And even electromagnetic theories, which you're so enamored by, they're requiring also assumptions, strong assumptions about discontinuous matter, in particular about electrons, right? And so he's trying to point out, look, the reality of atoms and electrons has been strongly supported by recent evidence. I'm not just doing speculative metaphysics about stuff we can't observe. We have good empirical reasons for thinking that these particles exist. Continuing on, he's saying, yeah, Kant's antimonies make it seem like this idea of atoms is self-contradictory. But Kant's antimonies and other laws of thought, they're subject to a bit of Darwinian evolution. They can change, they can be inherited. Again, most philosophical questions are speculative and overshoot the mark. So we're not being driven by these philosophical questions. Again, we're going back to what's well supported by physics. Future philosophy should avoid speculative questions and should change all laws of thought so that they don't interfere with scientific theories such as the atomic theory. Yeah, it was not well received, as I said, didn't get much press. The press that it did get was quite negative. 2 years later, you know what happened. Boltzmann gave up in the final, most dramatic sense of giving up. So I think this is really interesting to think about, and I just find it so fascinating, and especially applying it to our crisis now. Can we take lessons from this? So thinking about principles, yeah, I'm being very, how do I say it, broad with my definition of principles. I'm just saying any conceptual or formal feature of physical theorizing that's taken to play a role in the definition, construction, or justification of new theories. So I think I said enough about this yesterday, but especially important in the context of quantum gravity, right? Because they're being used both heuristically, but also as means of confirmation here. So it's not like we have this neat distinction between context of discovery and context of confirmation, as Richard shows us. So these ones I mentioned yesterday, the different ways we can use principles as guiding principles, heuristics. We can take them as a postulate, so assuming it from the outset and saying this is a core of my theory. It might be a criterion of theory acceptance, you know, being part of the definition of the theory, or being an external constraint upon it, but meaning that the new theory should not conflict with that principle. And they can be used as means of confirmation, you know, increasing credence in the theory. So if it features in any of these other roles, then it's a means of increasing credence. So I don't mean like that these are exclusive categories or that they're the only categories. I think principles can play any and all of these roles. Good. So you can see bit of a sketch as an example of different principles and different approaches. In loop quantum gravity, they're starting off with quantization as a postulate, so they're just kind of laying it down, this is what we're doing. Background independence is very inspiring for them, so they're using it not just as a guiding principle, but also as a criterion. Any theory of quantum gravity should be background independent, and also as a means of confirmation. If the theory satisfies this, then we have reason to believe in it. Discreteness as a criterion of acceptance. So yeah, I'm saying criterion. Criterion is the same as constraint here. And UV completeness as a means of confirmation. So UV being UV complete, meaning that it's not breaking down at any arbitrary high energies. Causal set theory, they're taking discreteness as their main postulate. And then using, of course, this means you're coming into a conflict with Lorentz invariance. So then recovering Lorentz invariance is their main kind of guiding principle and criterion of acceptance. We need to get this back when we get back our space-time. And string theory, of course, taking unification as kind of the main constraint. Also, the goal and the means of confirmation there. So you can see the different ways principles are being used in the different approaches. So I think we can then turn to evaluate these principles, assessing it as a constraint or as a guiding principle. You can assess it in each of its different roles, and it might be well justified in some roles, but not for others, right? So you can ask questions about where this principle is coming from. What's the physical motivation for it? What's it supposed to be doing for us? Some general philosophical motivations. Why is it desirable? And how it links in with other different principles. Are they conflicting? Do they match up? Do they mutually support one another or not? What happens if we drop it or put it back in? And then looking in particular approaches, is it doing what people want it to be doing in their own approaches? And like I said, I'm offering this to please join in my project. Pick your favorite principle, have a look at it, and start evaluating in different approaches. That would be great. I haven't managed to get my ERC grant to actually hire you on this, but I can try. I'll write up another application. So this is a nice slide that Neil's made showing some different principles and saying, we pick them out of a bag, see how they match up together. Okay, so where do we find our principles for quantum gravity? Of course, we don't really want these a priori, what was the term, philosophical prejudices influencing us, but that could be one place where people kind of have these principles in mind. We can look to empirical phenomena, such as cosmological data, and find out principles there. Current theories, these are the main source of our principles, of course, and these are the ones that I think have the most traction, especially amongst physicists. So unitarity, Lorentz invariance. The other main one is causality gets appealed to, how that ties in with Lorentz invariance as well, of course. So physicists are taking these as very core parts of our current physics. We should try to retain them. We should not expect a new theory to conflict with any of these, but something's going to have to give, right? Comes out very strongly with some of these black hole information paradox, where they lay out the principles and you show which one has to be rejected, which one can you reject, you go that way, reject the other way, go there. But also, theoretical results and combinations of our theories. When we're trying to put our theories together and we're getting strange results out, this might be indicating where principles conflict and lead us towards new principles. So far, as I said, I've been looking at the principles that are motivating the new theory and the principles that are taken to constrain it. I'm gonna skip some of these ones. Just to say, some of these principles seem to come up from problems that are arising from looking at our current theories, right? Different combinations of our current theories. So in a way, it's kind of problems that we've discovered in our attempts to find a new theory. So how are they actually kind of motivating when you've already started on the quest and then found this problem? So it's kind of leading you on the way, but it wasn't the actual kind of motivation to kind of kick you off. So I'd say these sorts of problems are only going to be problems to the extent that they prevent you from fulfilling the primary motivation. The primary motivation being our definition of quantum gravity. If you find a theory that satisfies that, then you've got your theory. So these other things, they're only going to be problems if they prevent you from satisfying that. Otherwise, it just seems like they are your philosophical prejudices. The big example that I mentioned yesterday being UV completeness. Why is it a problem if the theory breaks down at some high energy? As long as it's describing the domains that we expect quantum gravity to describe, where we kind of need it. It doesn't necessarily have to be a fundamental theory, but physicists have it in their mind that it should be a fundamental theory, meaning that it should describe kind of everything all the way down to as far as infinity. So that seems like a bit of a prejudice. So examining the principles in relation to the primary motivation, as I said, I think can be elucidating. If it's satisfying the motivation, if it's not satisfying the motivation, but you nevertheless think it's very important, then maybe you should kind of redefine what you mean by quantum gravity and be explicit about what it is you are looking for. Okay. So I'm going to turn now mainly to discuss the holographic principle. Are there any questions on what I said so far? So the holographic principle, here we go. This part of the talk comes from having a lot of discussions with Niels and Rasmus, so just to mention them too. So yeah, I think, as we said, there's kind of different approaches are adopting different sets of principles, but entropy bounds and holographic principles are really being promoted as quite strong contenders as being key principles for a new physics. And they're all quite, it's been taken up by almost every approach, so they're taken very seriously. Eric will tell you they maybe shouldn't be taken very seriously. So yeah, let's explore. They're used in different ways in different approaches. So Bigatti and Susskind here. New scientific ideas are usually characterized by simple organizing principles that can be expressed in a phrase or two. The invariance of the speed of light, the equivalence principle, and the uncertainty principle, and survival of the fittest are famous examples. Is there a comparable simple summary of the new principles which our science is now uncovering? Some people think that it's supersymmetry, others think it's duality, but the real world is not supersymmetric, nor is it known to have dual descriptions in any deep sense. My own view is that the lasting idea will be the holographic principle. And here's Raphael Busso. Progress in fundamental physics has often been driven by the recognition of a new principle, a key insight to guide the search for a successful theory. Examples again, principle of relativity, equivalence principle, gauge principle. These principles lay down general properties that must be incorporated into the laws. And he's arguing that any theory that incorporates the holographic principle must unify matter, gravity, and quantum mechanics. Therefore, it will be a quantum theory of gravity, a framework that transcends general relativity and quantum field theory. Smolin, again, saying, of course, it's always possible that the holographic principle is only a characterization of the semi-classical theory. But on the other hand, it's very possible that there are some deep clues to the structure of the fundamental theory, and that some version of the holographic principle might turn out to be a fundamental principle of the quantum theory of gravity. If so, it will be the first principle that's genuinely quantum gravitational rather than just being imported from our existing theories. So, as I said, this is really the number one principle that's being promoted by physicists who are interested in principles as solving the crisis. So here's hologram Dio to introduce some black hole thermodynamics, like a rainbow in the dark. I don't know, no one listens to Dio, do you? Okay. This is going to be really quick. So the black hole entropy, of course, being motivated by, firstly, the no-hair theorem. When you drop your coffee cup full of entropy into the black hole. The stationary black hole, it's being characterized completely by mass, charge, and angular momentum. So when you've dropped it in, where's the entropy gone? It seems like the second law of thermodynamics has been violated, right? Because there's no increase in entropy of the black hole. Entropy of the universe has gone down. And secondly, the area theorem, which is the recognition that the area of the black hole horizon never decreases. So from this, you can see it resembles the second law of thermodynamics and suggests a way of saving this second law of thermodynamics. It also suggests an analogy between the black hole area and the thermodynamic entropy because they're both never decreasing. So Bekenstein thinks, yeah, this suggests a way to compensate for the loss of entropy when we've dropped in our coffee into the black hole. Maybe if the black hole itself has entropy and this is proportional to A, then we see the area grows, the mass grows because you've dropped in the entropy. So this is what he proposes, that although kind of the second law gets violated, we have this generalized second law, which includes not just the matter entropy, but the black hole entropy. And this one is the generalized second law that's going to be what we're working with. This one is not going to get violated. So it was a suggestion. And from this, you also kind of get led to analogous laws for the rest of black hole thermodynamics, right? So we get, if we're taking the entropy of the black hole seriously, then by the first law of thermodynamics, requires that the change in mass is equal to the change in the entropy. And this is how you define the black hole temperature. And this one, yeah, change in mass being change in the surface gravity and the horizon area. So Hawking then does this famous calculation, which seems to confirm that the black hole has an actual temperature. So you can see this one only works if there is a temperature assigned to the black hole, and before that, there was no reason to suppose it. So it was just an analogy. But once he's kind of done this, it's really given weight to this as black holes being thermodynamic objects, and it's also a quantum process. So once you've got this temperature, we can fix the Bekenstein entropy formula as being equal to the area over 4. Okay, like I said, that was really quick, but it has the consequence, of course, that black hole is radiating, the mass is decreasing as it's radiating, the area is decreasing, which means that this area theorem, which was kind of the motivation for proposing this in the first place, is no longer valid. And the generalized second law will still hold, right? Which kind of means that there will be a restriction on the entropy of matter available. And this is where the idea of the entropy bound comes from. So it's going to be limited by this relation. So this suggests if black holes are thermodynamic objects, well, we know from ordinary thermodynamic objects that we have these microstates. Maybe there are microstates underlying GR, right? So GR might be analogous to thermodynamics, a phenomenological theory, rather than a fundamental theory of little constituents. And so it's kind of prompting this search for microstates of space-time. And then the Bekenstein-Hawking entropy is giving us a measure of the number of microstates. And the new quantum gravity theory is expected to recover and explain this. And as I said, this is being treated very, very seriously. A lot of approaches are taking this number as a constraint. We need to show how we arrive at this number. So string theory and loop quantum gravity have managed to derive this number with their own frameworks, but it's only for certain conditions and certain types of black holes, so neither of them have a general result on this. But they're working towards it, you know, it's a motivation. So yeah, that was the way too quick introduction to black hole thermodynamics, but I'm assuming people have heard that before. Yeah, okay. The entropy bounds then. So it seems like we have some upper bound on the entropy of matter. But like, what is this bound? There are different proposals for what it actually could be. Got the Bekenstein bound, the spherical entropy bound, space-like entropy bound, covariant entropy bound, weak entropy bound, all kind of different proposals trying to find the correct entropy bound. So this work is following this paper by Bosso from 2002 on the holographic principle. I think it's just called the holographic principle. I was a big fan of this paper, and I just met him. It was this Saturday right before coming here. So there we are backstage at this philosophy festival. Good news is that he's really cool to talk to. So this is taken basically from his paper, the way he presents it. So the Bekenstein bound, you calculate this appealing to the Dirac process, which is where you have your matter system, your cup of coffee, and you're slowly lowering it into the black hole. And this is what you arrive at. So this limit on the entropy, which is based on this radius, circumferential radius of the smaller sphere that contains the system. So you've kind of put this, what was it? Boundary, little sphere holding your little coffee cup. And that's what you arrive at. So it means that this area of space-time has some maximal amount of entropy that can be held in that area. And this one, yeah, it seems like it holds in other systems. So it might be hard to define this region when we have strong curvature, but under some special cases, it holds for strong gravity. And here, it hasn't been ruled out, but you can see it's a bit limited. So then we move on to this spherical entropy bound, which is where instead of dropping your little entropy into the black hole, you have it and you convert your coffee cup into a black hole. And then from the generalized second law, you arrive at this entropy bound, where A is some suitably defined area enclosing your system. This derivation, it's quite heuristic, saying it's resting on quite a large number of strong assumptions. But Bosso is thinking then, well, maybe this spherical bound is a special case of a more general bound. And then he's going looking for this more general bound. So the limit on the amount of entropy we could have in a certain area. So the most straightforward generalization of this spherical entropy bound is this one called the space-like entropy bound. So the entropy contained in any spatial region will not exceed the area of the region's boundary. So you can see there is our region, and that's the boundary, and it's saying that it's limited by the area of this boundary. And as you can see, this is not successful. So why isn't it successful? Well, it's not covariant, so it's depending on a specific slicing. You can see there, it's on a specific slicing. And it's also got many counterexamples where this just doesn't work. So one counterexample that he considers is this collapsing star, where we have a spherical star with a certain amount of entropy. It's burning out, it's undergoing some catastrophic collapse, becoming a black hole, crunching down to a singularity, where the area has gone to zero, but the entropy has not gone to zero. Because according to that, it's still at least what you started with. So this is a counterexample to it. So he's arguing we need to find the correct generalization of the spherical entropy bound. So his heuristic is like, okay, imagine we have this star that's crunching down catastrophically. What if we want to take a photo of the star just before it crunches into the singularity? So you take your little camera, make a snapshot, and what do you see with the snapshot? Well, the light that you're photographing doesn't have enough time to completely cover the entire area of the star before it crunches. So what you end up with is that the area, the entropy of the area kind of traversed by the light is always less than the area of the star's surface. So that's the hint there. So that's how he ends up with his covariant entropy bound. And yeah, a bit of a weird idea. It's based on this idea of light sheets. So you can construct these light-like hypersurfaces called light sheets for any 2D surface. So here we've got our surface B here, and it has area A. And the light sheets, so these are the light rays emanating from a point on that surface, right? But not all of the light rays from the surface are light sheets. It's only the ones that are going in, like converging. So F1 is a light sheet and F3 is a light sheet. But these ones that are expanding away, F2 and F4, those are not light sheets. So he's ended up arguing that then the total matter entropy on any light sheet is less than A/4. And he thinks this is the correct bound. You've arrived at it by a pretty strange line of reasoning, right? But he's arguing that it works. This is argument for why the light sheet entropy is the entropy of the matter system. I won't go over that one. But basically how he's arguing for it is just that it works. He's saying this appears to hold universally in nature, which just means, you know, all the calculations we've done, we haven't found any counterexamples. It holds for arbitrarily physically realistic matter systems and arbitrary surfaces in any space-time that solves Einstein's equation. So it's very general. It can be saturated, but he's found no cases where it's being exceeded, so it seems to hold. It also reduces to that spherical entropy bound from Bekenstein, as we would expect, and he argues that it also implies the GSL. So we can show that it directly kind of goes along with the generalized second law. So yeah, we also have another contender, the weak entropy bound from Smolan and Markopoulou. I haven't looked into that one so much, but it's another possibility. So yeah, we have these different bounds, and we're interested in how they could possibly guide us in quantum gravity. Any questions on that? Okay, good, yeah. You can find the paper anywhere and see how he argues for it in a bit more detail than the way I've presented it. So maybe this entropy bound is something we should be taking seriously. Maybe this bound is the principle we're looking for, you know. It's quantum gravitational because it's involving quantum and gravity constants. It's surprising, you know. We want a bold new principle that's going to surprise us and indicate something that we weren't expecting, given our current knowledge of the universe. Of course, we'd expect the entropy of a volume to be proportional to the volume, right? We wouldn't expect that the entropy of a region is constrained by the area of the surface bounding that region. This is very surprising. It means that most of our physics is always going to be overcounting. So it seems also very mysterious. What's the explanation for this? For this covariant entropy bound, as I said, he's arrived at it by this kind of strange line of thought, but he's arguing that it can't be derived from our known laws of physics. So we need some kind of new physics. This is indicating something in the same way that, surprising empirical results come in conflict with our theories. It seems like this very theoretical principle is coming in conflict with our theories. Right. So we need an explanation for it. So I think it's quite interesting because, the principle, we've arrived at it from black hole thermodynamics, but now he's saying it can't be derived from black hole thermodynamics. So it's kind of outstripped black hole thermodynamics in a way. And I think black hole thermodynamics itself has a bit of strange motivation, right? You know, we're being motivated by trying to preserve this area theorem, and then we're violating it. And we usually don't think of the second law of thermodynamics as a fundamental either, right? And yet, you know, here we are putting it on a pedestal and saying that we have to keep it. And it's open to statistical violation. So how is it a true fundamental law when it can be easily violated? So I think that's quite interesting. So it seems like, how are we justifying it? Just by the fact that it's holding true in all the calculations we've done, these calculations being remote from empirical tests, the calculations being done based on our current theories, the very theories we're seeking to replace. So it's a bit of a strange way we've run into this. And as a principle of quantum gravity, we've got these bounds implying, a radical reduction in the number of degrees of freedom that are needed to describe nature. It's conflicting with our current accounts. Quantum field theory is really overcounting, of course. It's giving us the wrong answers. And the entropy bound is also in tension with the principle of locality, but I won't go into that. So it may be conflicting with some other principles we want to look at, right? So how do we use it? Well, maybe we say, well, it's a strange result. It's implying that our current physics is wrong, it's incorrect. We need new physics to explain this bound. Or we might side with established physics and say, okay, we're correct in what we're thinking about entropy. This new result is just wrong. But then how do we explain this result? I guess the new theory we find will give some explanation of it, but for why it's wrong. We might think that it's just an artifact of our semi-classical theories, so in that case we wouldn't expect to recover it because we just don't have any evidence for semi-classical gravity being correct either. So different theory attitudes to take, and I guess most people are going with this first one. It's exciting, it's mysterious, it's going to show us something new. Okay, so the holographic principles. I'm not going to talk about the information paradox, except to say that this is where the holographic principle kind of got its inspiration for. That when, Hawking radiation, our black hole radiates away, all the entropy has been lost, it's destroyed unitarity, we'll end up with this paradox. One proposed solution is that the information isn't being lost, it gets stored on the horizon area. And then the preservation of unitarity motivates this holographic principle. And that's from 't Hooft there. So that's the motivation for the holographic principle, that the information gets stored on the area of the horizon. And it finds, of course, restatements that the description of a volume, so any kind of volume of space, your bulk, can be equivalently defined on a lower dimensional surface bounding the volume. So that's the statement of the holographic principle. But then people have different formulations of what they actually mean by the holographic principle. Maybe that the full theory of quantum gravity can be reformulated as a theory all of whose degrees of freedom are defined on the boundary. So Susskind is going with this. The number of possible states of a region of space is the same as that of a system of binary degrees of freedom distributed on the boundary of the region. And then the concrete example being the ADS-CFT duality. So we have different conceptions of the holographic principle. Boisseau is saying that the holographic principle is the claim that the origin of the entropy bound is to be found in the new theory. So he's kind of not talking about the holographic principle, he's talking about this entropy bound. Smolin is saying that the bounds provide the limit on the number of degrees of freedom, while the holographic principle provides a dynamic, so it tells us about the nature of those degrees of freedom. So seeing the entropy bound as being the limit, the number, gives us the number, and then the holographic principle is the explanation of that number. So it's not, this is Smolin still, not a relationship between two independent sets of concepts, bulk theories and measure of geometry versus boundaries and measures of information. It's the assertion that in a fundamental theory, the first set of concepts get completely reduced to the second. So to kind of explain it in terms of information. But, I'm thinking what it's showing us really is that it's not kind of the duality that should be taken as the principle here, it should be the entropy bound. This is what we want to explain, the entropy bound, right? So looking at this relation between the entropy bounds and the holographic principle, Rasmus Jaksland and Niels Linnemann, of course, they're actually arguing that the existence of the entropy bound doesn't have to do with the holographic principle. Why? It's because entropy bounds are intra-representational. So we have a single description, a single theory, and this bound is giving us the limit of number of degrees of freedom in that theory, one picture of the universe, one universe. Whereas the holographic principle is inter-representational. So we're connecting two separate descriptions. So they're saying, therefore, the existence of the entropy bound doesn't imply that there should be a holographic principle, because on the one hand, the entropy bound is on this theory defined on the surface, and if we want to actually motivate it as telling us something about a more fundamental theory. How is it doing that? You have to cross over into the other theory. So thinking about the heuristic role of dualities here, Sebastian de Haro is saying there's two different functions of dualities. A theoretical function, where we're kind of using the duality by developing a common core theory that's on both sides, right? So the stuff that both sides of the duality agree upon, we extract this information and develop a common core theory. But when you're doing that, you're learning about what's common to each of these theories, but you're not learning about something beyond the duality. You're not going outside of that picture. But if we want to find a new theory that's kind of going beyond this common core theory, we need to actually break the duality. So we kind of split them. We say that they're not equivalent anymore. And then you go looking for some more fundamental theory, and you show from this that the duality gets recovered afterwards, approximately. So Rasmus and Niels, they have a similar idea, but also disagree with Sebastian here. They're thinking, as I said, holography is inter-representational. Yeah, I should have explained the ADS-CFT. It's easiest to think about in the context of the ADS-CFT, right? So on the one hand, the dualities is telling us about the relationship between features on each side. So we've got these two different theories. One has gravity, the other one does not. One has entropy, the other one does not. And it's telling us about the relationship between the two different theories. But it can't tell us anything kind of beyond that. If we want to actually kind of work where we have a description that's including both gravity and entropy, we need to break the duality again and put it into a single theory. So we want the intra-representational relation. So they're arguing we use the holography to get a theory without the holography, without the duality. And in that case, it doesn't make sense to recover the duality. So against de Haro there. So I think this is their example to kind of illustrate, hopefully it helps illustrate, I don't think I'm doing a good job here, that these inter-representational relations, they're not heuristically useful. We have this Ryu Takanagi formula, which, it looks just like the black hole entropy formula, and it's been derived, using the ADS-CFT, it's the entanglement entropy, but it's not the black hole entropy. You're looking at this and like, yeah, we've derived the black hole entropy from entanglement. But the problem is that it's inter-representational, meaning on this side, we've got what's this one? I always get confused. This one is the CFT, right? So that's your conformal field theory. That's your quantum stuff. And then on the other side, so on that side, you don't have space-time. You don't have the gravity. Here on the other side, you have gravity, you have your black hole, but you don't have the entropy, because it's living in a different theoretical space. So because of this, you can't explain one in terms of the other. They're two dual theories separate from one another. If you want them to speak to one another and get a derivation of the black hole entropy in terms of its area, you need to break this and turn it into an intra-single theory representation. Yes.
Would Niels and Yoxlin say that Boltzmannian physical mechanics doesn't explain thermodynamic entropy because they're two different theories?
No, I think they live in the same world, right?
They're talking about representation, not worlds.
Yeah. But they still, yeah, I see what you're saying. But it's still kind of the same space-time. Maybe that's the idea, something like this. Same arena.
I haven't read this paper, but the way, at least in presenting it, they're talking entirely about theories and representation, not worlds and space-time.
The world defined by our theory, yeah. Yeah, I'm not sure they consider that. I think it's only talking about these dual theories, where we have equivalent, was it physically equivalent, but telling us different things that exist. And I guess already thermodynamics and statistical mechanics are not equivalent in that sense, right? It's not like we're choosing one or the other in that case, and they can talk to one another. These ones don't talk to one another, and you only kind of need one or the other. So, yeah, I can see the parallels, but I guess you'd push on the differences there. Okay, so I think that's kind of it, and we should take a break. But yeah, just to think about, yeah, these entropy bounds, maybe they are surprising and useful. How do we use them? They can be taken as a guiding principle. We could use it as a postulate. Maybe it's a criterion of acceptance. We need to analyze this. Must quantum gravity explain the origin of the entropy bound? If so, which one? Must it predict the number of microstates? Because if it's going to be a constraint, then it would be held very strongly. We can use it as a means of confirmation. So if our favorite theory of QG has managed to get a derivation that recovers the bound, then it seems evidence for increasing our credence in the theory. So it is being used in different ways, in different approaches there. Yeah. And this one's on the holographic principle. The first slide was about the entropy bounds. So again, thinking about the holographic principle, how can this be used to guide our search for a new theory? We need to do some work on that if we're going to show that it can be heuristically useful. Can we take it as a postulate? I don't know. I guess so. Criterion of acceptance seems a bit less plausible. But again, it's being appealed to in some approaches as means of confirmation, right? Like especially in string theory, they've got this ADS-CFT duality, and they take this as like the most pure example of the holographic principle because it's supposedly non-perturbative. So they're saying, we've got it. This is a means of confirmation. All right, good. Yeah, I should have explained this before instead of just skipping it in case people haven't seen this. So I was talking about the holographic principle and how it might be conceived of in relation to the entropy bound. Whether the holographic principle is motivating the entropy bound or meant to explain it, which one is more basic. I'm arguing that we should look at the entropy bound. But this is the main example of the holographic principle that people appeal to. So the principle itself is supposed to be more general, but this is the one kind of representation that people really say is the most concrete one. But again, of course, it's conjectured. We know that it doesn't apply in our universe, this one. It's come from string theory. And basically on one side, so you have two different theories. One of these theories is called the ADS because it's defined on an anti-de Sitter space. So this is a string theory defined in a d plus one dimensional ADS anti-de Sitter bulk space-time. This is your theory with gravity. So it's living inside this tube. It's in the volume, the bulk. And then the CFT is your conformal field theory, which is a quantum field theory without gravity. And it's defined on the surface of this bulk region, right? So it's got one less dimension. And the claim is that Mauthausen has shown they're observationally equivalent to one another, which means in these dual theories, any kind of observable prediction you can get out of one, you can get out of the other. And yet, as you see, they're making very different claims about what actually exists. How many dimensions are there? On one theory, we've got D. On the other theory, we've got D plus 1. In one theory, we've got gravity. In the other theory, we don't. And then trying to explain why it is that we're able to kind of do all the same physics on the boundary with the fewer dimensions. Then it seems like this bulk description is redundant in a way. It's kind of, you don't need that much information to get the physics out, to get our empirical stuff is the idea. So many physicists are kind of taking the lower dimensional theory as being more fundamental, but if they are equivalent in a certain respect, you know, what's the motivation for treating one as more fundamental than the other? Okay, were there any questions on, how do I get out of this? On where I finished, which was there, right? I've forgotten how to hide that. Was it there?
Yes.
Okay, cool. So I'll now talk about the singularities. Oh, no, I can't skip them. So this is based on a paper I wrote with Sebastian Di Haro, 4 attitudes towards singularities in the search for quantum gravity. So I will skip these ones, but basically the same sort of thing, you know. Singularity resolution is taken to motivate a new theory. A guiding principle. Often it's taken also as a constraint. We're expecting this new theory of quantum gravity must resolve the singularities present in our current theories, because those are problems that are going to be solved by the new theory. So it can also be presented as a means of confirmation. Hey, look, we've gotten rid of these pesky black hole singularities, pesky Big Bang singularity. We've got an explanation for what's actually going on. And usually this is because the singularities are viewed as an incompleteness of our theories. You know, it's not giving us answers to questions we want to ask. It's not telling us what happens, you know, in the regions where these singularities occur. Our theory is incomplete or it's breaking down. Therefore, we need a new theory to complete our description of nature. So you'll see lots of quotes like this, of course, basically to the effect that space-time singularities represent breakdown of space-time, that general relativity contains the seeds of its own destruction. This very figurative example here, you know, that the singularities are unavoidable. It's inevitable that they're going to develop in such a theory. No one sees an escape from the density of mass energy raising without limit. It's getting higher and higher and higher until we can't calculate it anymore. A computing machine going step by step this dynamical evolution. Eventually the geometry is becoming so strong that you can't compute anymore. Smoke begins to come out of your machine. Kiefer, that GR cannot be true at the most fundamental levels, clear from the singularity theorems. It signals a breakdown of space-time. And this is a standard view, even by Hawking, that the theorems in this and earlier papers probably indicate not that the singularities actually occur in our universe, but that our theory has broken down. So we need a new theory. But on the other hand, we've got some people who are a bit more skeptical, you know. Urbino, who's the expert on space-time singularities, saying, well, what about we take seriously the fact that general relativity, the existence of space-time singularities, need not mean that it contains the seeds of its own destruction. Maybe this generalized horror singularity is not justified. We have different types of singularities. Maybe we shouldn't be afraid of all of them, and especially not in general. And he even goes on to argue in a later paper that we shouldn't be viewing them as seeds of the destruction of GR. Maybe they're seeds of prediction. Maybe we can take these as a prediction of GR. So, do the singularities represent incompleteness of our theories? It seems like physicists are saying yes. And philosophers are, more questioning. They're saying, well, in what sense is it a breakdown of space-time? In what sense is it an incompleteness? We need to figure out what you mean instead of just saying it's going to break down. How does it break down? So we went looking, in what sense can we say that GR breaks down? And we're arguing that there are different attitudes you can take towards these singularities in regards to QG, whether they're motivating quantum gravity or not. So, yeah. Oh, yeah.
Going one step back, I missed the last bit.
This one?
Okay, sorry.
Good. So yeah, in the paper, we start off by talking about, we do both basically. We do the space-time singularities in GR, but we also have singularities in quantum field theory. And probably won't go over the quantum field theory for you today and focus on the GR ones. Maybe I could have given another talk as well. But now let's start with the GR ones, right? So what is the singularity in GR? Well, there are pathologies, and there's various different types, so different ways in which our spacetimes might be pathological. So Urbino is saying, yeah, they're very conceptually distinct, but interrelated, and they kind of infect our spacetimes. And the Penrose-Hawking singularity theorems show that such pathologies are inevitable under very physical, reasonable conditions. Notably, we have black hole singularities, and we have a Big Bang cosmological singularity. And there's two main classes. You can see Eric's article on this. Geodesic incompleteness versus curvature singularities. And also, does one imply the other? So on the geodesic incompleteness definition of singularities, we say that a space-time is singular if and only if it contains an incomplete, inextendable time-like geodesic. So basically this intuition that we have our space-time and there's just like a missing point of space. So you're traveling along your geodesic and then it stops somehow. But does this represent an incompleteness of GR? Is it a breakdown? So Eric says that, well, it's pretty unclear here. If we're talking about geodesic incompleteness, we have this intuition that it's a missing point of space, but you actually can't think about it that way because a missing point of space, you're thinking of that as a point in space that's just not there. But then if you can locate it in the space where it shouldn't be, you've located it and it's in your space. So you can't think of it as being located anywhere in the space. As Urbino puts it, look, there's no singular points of space-time where the laws of general relativity fail to apply. You know, the whole of space-time is being described. Okay, these missing points aren't being described, but where are those? They're not in our space, so there's nowhere where the laws are failing. So Meissner as well, there's no reasonable point at which to anticipate a failure of the theory. So how is it a breakdown of GR? But it seems like there's still a physical worry here. Hawking and Ellis put it like this. We could have it that there are freely moving observers or particles whose histories just don't exist after or before a finite interval of proper time. So they're thinking of this as being even more objectionable than the infinite curvature. So they're taking this definition of singularities when deriving the Penrose-Hawking singularity theorems as well. As Eric puts it, if we have this geodesic incompleteness, it seems like particles just could pop in and out of existence right in the middle of our singular space-time somewhere. Space-time itself could simply come to an end, but there's no fundamental physical mechanism or process known that could produce such effects. So it seems it's still physically problematic, even if we can't say where this is occurring. So trying to figure out in what sense this could be an incompleteness, the main worry seems to be that it leads to a lack of predictability and determinism. And in this way, it could be that our theory is incomplete. Why? Because if the breakdown of determinism is visible to us, then we get kind of sprayed with these random effects. But GR, we've set up, we know that there aren't these random effects, and we've built our theory in such a way that it's supposed to be deterministic. And now it's saying that there is the possibility of this indeterministic influences. That's a problem if we can see them. So that's what he's arguing here, and that's what he means when he says the laws would perversely undermine themselves. So it's not the indeterminism that's the problem, it's the fact that these laws are supposed to be deterministic and they're producing indeterminism. So it's undermining itself. It took me a while to figure that out, so hopefully that was clear. Like why he thinks it's a problem. So we have an inconsistency here between determinism and indeterminism. And in his book he says, yeah, green slime can emerge, any kind of random things. Like TV sets of Nixon's speech just popping into existence. So we have some sort of inconsistency related to indeterminism, but does this motivate the need for a new theory? Well, I think maybe or maybe not, right? We might think, well, what do we mean by determinism? If we have different senses of determinism in GR, which I won't go into, you can look at these papers by Julius, Chris Menkins, Chris Wittrick here. So if GR is already not deterministic, then the presence of indeterminism or the prediction of indeterminism isn't inconsistent with the theory anymore. So no problem. Maybe you're just not bothered by indeterminism, so that's not motivating you to look for a new theory here. And especially if strong cosmic censorship holds and we never see this indeterminism, it's never going to bother us, then again, it's not going to lead us into this kind of inconsistency, the paradox that's being set up, where we've started off without these effects, and then we have these effects, and now we're saying, yeah, we might have these effects, but we never see them, so there's no inconsistency anymore. So this is where the cosmic censorship comes in, different proposals here just trying to save us from observing these horrible creatures, right? So weak cosmic censorship, it hides the singularities behind the event horizon. So they're not naked, they're hidden from us, we don't see them, they get, censored. So the outside observers are shielded, so we don't have this inconsistency anymore. We're never going to see these random effects, green slime. But of course, there's still a problem here, because we still, if there is space-time beyond the horizon, as we're expecting, and GR is not giving us determinate answers about what occurs there, then the theory is incomplete. You could still fall into that black hole and see the random stuff, right? So this isn't going to do it for you. This isn't going to save our theory. So this is where the strong cosmic censorship comes in, which says that this breakdown of determinism is not just at the event horizon, rather what occurs is beyond this Cauchy horizon. So this is inside the event horizon, and it's beyond this surface that the Einstein equations no longer give you a unique solution. So this is where the problems are occurring beyond this horizon. So yeah, I just borrowed this slide. You can see here, just as an explanation. So if you have this space-time, and you have this point P here, from this initial data, you can determine what happens at P, right? So this one's deterministic. But if you have this space-time and you're looking at point PQ, here you can see that your data here, kind of later on here, it's intersecting with the singularity, and so you're not getting a unique solution for what's happening here at P2 given the data anymore, because it's kind of gone beyond. So this is going to happen whenever there's the Cauchy horizon. And Penrose's idea is that, okay, this is where the problems are, maybe these horizons just don't form. So saying that maybe the appearance of such a horizon in Schwarzschild black holes is not generic. So some way it's unstable, meaning that under kind of small perturbations, these just don't form. So it's so unstable that any passing gravitational waves would prevent their formation, and instead what you end up with is a space-like singularity, and there your metric is inextendable, so you're not having space-time after there, and ensures that there's no violations of predictability that are detectable even by local observers. So even if you're falling in, you're never going to see the random green slime. Yes, so the singularities get rendered harmless if this holds. That makes sense? So it seems like whether geodesic incompleteness is problematic for determinism rests on the fate of this strong cosmic censorship. Hawking bet that it's true, but apparently this debate is still open. We don't know whether this holds or not. Yeah, I found some interesting cases, but I won't go into those. So again, it seems like geodesic incompleteness, whether it's motivating a new theory or not, whether it's showing that GR breaks down or not, based on this inconsistency, is depending on a number of factors. So it's not kind of necessary. What about the curvature singularities? So the curvature singularities, this is where something is blowing up. One of your quantities is going to infinity, maximal curvature is blowing up. or some other quantity related to the curvature. So these are what physicists find a bit more worrying, and they're a bit less discussed by philosophers. And we're kind of thinking why they're important to look at is that they can still, the curvature singularities can still be dangerous even for strings or extended probes. Whereas for the geodesic incompleteness, if you have an extended probe, you might be insensitive to the geodesic incompleteness. So these seem a bit more worrying. Why are they worrying? It's this idea that if we have GR, and we're including some small corrections, so kind of higher curvature terms, which could be there, but normally we don't need to use them. Such a theory will, under most circumstances, just be equivalent to GR. But if you are, where are we here? If we're far away from the singularity, yeah, these extra curvature terms are going to be negligible, so the theories will be equivalent. But as we're moving closer to the singularity, if you compare this effective theory with GR, they're going to give you different results. So it seems like this is the way that physicists have in mind that the curvature singularities predict that GR breaks down, because we're getting this inconsistency between GR and the expected quantum gravity effects that are going to appear close to these curvature singularities. So it's a breakdown from what we're expecting to happen in GR. So, sorry, GR is failing to describe what we expect to happen in these regimes. So this is the main argument that physicists say curvature singularities are problematic for GR. Was there questions on that? Maybe. Going to skip the QFT stuff in the interest of time, I think. Yes, definitely. And just move to these different attitudes we can take towards singularities. Oh, not this again. Which one is it? Asconti. Learning some Italian here. So, do singularities point to the need for quantum gravity? So in the paper, our strategy was just to go through the literature and see the different arguments and attitudes that people have towards singularities. So it's not like we were doing, like, exploring the philosophical possibility space. We're actually doing a survey of the physics literature and seeing the different attitudes that people take. And there's 4 different attitudes, only one of which is taking them as motivational for QG. And of course, different types of singularities we can expect will receive different treatment. So it's not meant to be like a, if you have this attitude towards one, you have that attitude towards all of them, you can choose different attitudes to take for each. So that's important to keep in mind. So yeah, it's just a discussion of the examples and how you can have these different approaches to them rather than doing an evaluation. I haven't done the evaluation step to say what's the appropriate attitude to take. So attitude 1 is that we don't need a theory of quantum gravity to resolve our singularities. Rather, we can do so at the level of current physics, so not needing a more fundamental theory. So for instance, if you're talking about the divergences in quantum field theory, they arise in conventional quantum field theory from kind of the assumptions and postulates that are going into this. But there are proponents of axiomatic quantum field theory who say, yeah, regular quantum field theory is very ill-defined, not mathematically consistent. Let's come up with some new axioms that is not supposed to be a more fundamental theory than quantum field theory. It's supposed to be a correct theory of quantum field theory. So that is still meant to be quantum field theory, being a combination of quantum mechanics and special relativity, so you're not moving to a deeper theory. And they're doing that in a way that the singularities won't arise. So that's an example of this attitude. Another example is if, as I mentioned, this kind of smearing out of your point particle. If you don't have the points, you're not going to have the singularities. So you can do it this way, kind of within GR, without moving to a more fundamental theory. But you still need to modify your theory in some sense. We also have kind of higher dimensions. So I think I had a slide on this from Gibbons, Horowitz, and Townsend. They're saying that, okay, we have some black hole spacetimes that in our regular 4 dimensions, they look like they're singular. But when we move to a higher dimensional theory, these are not actually singular. So by introducing these extra dimensions, you can get rid of the singularities in our theories. Even within GR is the idea. So where are these extra dimensions? Of course, they're compactified somewhere. This one allows you to evade the singularity theorems of Penrose and Hawking because you've moved to the higher dimensions, but it's not a general mechanism. Another way is this gravistars. So these are kind of cool. So I just put a couple of slides on those. Gravistars, an alternative to black holes. I love it. So of course it's short for gravitational vacuum star. What you have here is not a black hole. It's a shell of some ultra relative, some interface with some ultra relativistic plasma, and inside it, it's kind of like a gravitational Bose-Einstein condensate. It has no entropy on the inside, but it's got some sort of dark energy-like behavior that's kind of keeping this shell spherical. It's not collapsing, so there's no singularity inside. But it looks like a black hole from the outside. So this is the idea here. And it can kind of behave according to the laws we expect of black holes, except for those singular and the event horizon aspects. And they think this could also explain the beginning of our universe. And another very recent proposal, so people are still working on these, came out in 2024, where they're having a nesting of gravistars, one inside the other, like a Russian doll here, and they're calling it a nest star. They're like, yeah, this is a solution to Einstein's equations. We don't know how it could be produced in our universe, but it is cool. Come on, we gotta say it's cool. And apparently there's some Italian interest in this, so you can have a look at these as well. So that's one way we can get rid of the singularities without moving to a quantum gravitational theory. What about attitude 2? This is where we say, yeah, we do want the new theory, and quantum gravity is going to resolve these singularities. So the singularities are going to stay in our current descriptions. They're only going to be resolved at the level of quantum gravity. So people find this very motivational. Yeah, you know, we have these singularities in our theories. Let's look for a new theory. So it's a guiding principle. It might also be used as a criterion of theory selection, meaning that we won't accept a theory unless it's getting rid of these singularities for us. And it also might be that you don't start off being motivated by the singularities, but once you've developed your favorite approach to quantum gravity, it's got a natural mechanism that resolves your singularities for you. And in this case, you could appeal to it as non-empirical confirmation, evidence that your theory is, on the right track, credence in your theory gets increased. So it can be used as non-empirical confirmation as well. And yeah, this is the attitude of most people working on quantum gravity. So they're thinking that the singularities are telling us something physical, even if the singularity itself isn't supposed to be something physical. So it's telling us about the breakdown of our theories. Kind of, a point where we can expect new physics. But as I said, it's not really that they think the singularity is a physical event. Rather, it's signaling the need for the new theory. I'm going to skip that one, actually. So, some examples. Actually, maybe I'll go back to that one. So, because I think this minimal length is pretty interesting here. It's like, if you can introduce a minimal length, it's going to resolve your singularities because, as I said, you are not going to the point anymore. You're not going to kind of the locus anymore. And this gets motivated quite a lot because there were singularities in our previous theory that got solved by quantizing. So kind of instabilities in the hydrogen atom, quantum electrodynamics, that it kind of blows up, it's unstable, but that got solved once we got rid of classical electrodynamics, quantized it, and got quantum electrodynamics. So some indications, people are being motivated by analogy here, that, okay, the singularities in GR, if we quantize them, we can get rid of our singularities. So it's motivation for quantization, as I said yesterday. And I think this is pretty interesting too in regards to the non-renormalizability of gravity in the perturbative treatment, because there, again, by analogy with previous theory, Heisenberg in the 30s and 40s was looking at the then fundamental theory of interactions, being Fermi-4 theory. It was non-renormalizable, and so he thought, well, maybe this is indication that there's a minimal length here that would save our theories, right? But that's not what happened. There was not found to be a minimal length. Instead, we found that our theory was an effective description, and we got led to electroweak theory. So by thinking that there's a minimal length, you might be being misled here. It's more like if there's a minimal length that would be conciliant with other kind of predictions, it would solve your problems. But the fact that we have singularities isn't motivation for taking a minimal length. So some examples here. In loop quantum gravity cosmology, they're taking some equations in very simplified models of loop quantum gravity cosmology, and they're showing, Bergerwald and collaborators here, that if you evolve, zooming backwards through the Big Bang, you're seeing kind of the universe becoming hotter and denser, but then it's not breaking down at the Big Bang singularity. Rather, you can actually proceed through, and you end up with kind of an expanding universe on the other side. So here, there is no breakdown, there is no singularity. Other models here, like a dynamical resolution, where we get, exactly these kind of bounce models of cosmology. And what do we got here? Yeah, maybe I skipped this one. So that's some examples of attitude 2, where we can develop our quantum gravity models to get rid of the singularities, particularly the cosmological singularity. They want to find out kind of what happened at the Big Bang. If GR is breaking down there, it's not giving us answers about what happened at the Big Bang. We develop our theories that give us a story about what actually goes on. The next attitude is peace with singularities. So here we are not resolving them in our current theories, and we're not looking to quantum gravity to resolve them either. Rather, we like the singularities. We're at peace. We are tolerant. So there might be reasons for keeping singularities in our theories. So perhaps they are predictions of the theory. Maybe they're explanatory or they're required for stability. So this first example, where they're treated as predictions, is what I mentioned before. Meissner had this idea and Ehrman picked up on it, saying that we can treat them as predictions, a source from which we can derive much valuable understanding of cosmology. So this is very striking compared to the other attitudes, right? How do we consider them predictions? Yeah.
I have to remark, because it really doesn't seem well known. In Penrose's 1969 paper, where he first proposed cosmic censorship, he actually did it specifically with this in mind. He was saying singularities may be great. You know, I hope we see singularities, because they might teach us something new. So Penrose didn't propose cosmic censorship because he didn't want singularities. He actually proposed it as a way to try and pinpoint what might be truly novel about singularities.
Okay, that's cool. I like that. That's cool. So Hawking himself was taking it as a prediction, and Penrose as well. I know Hawking always changed his mind a bit as it went on, but at some point.
Penrose was very excited about the possibility of observing singularities.
Okay, so it's not just Meissner here. Yeah, I think we should look into this. The idea is that if we trust GR and all its other predictions, it predicted many surprising things, and we went out and we found, gravitational waves. We weren't expecting this. So why, if this theory is very well confirmed, maybe it is indicating these as predictions as well. But then what does it mean, right? How could we test it? How do we determine whether these singularities actually exist or not? Of course, we have to look at kind of large-scale global properties because we can't pin down where the singularities are in our space-time. But Ehrman is saying that it might not be impossible in principle. And I think this is quite interesting, because it seems now that physicists are a bit hostile towards singularities, especially infinite ones. The usual argument, kind of the only argument that I've seen, is that infinities are unverifiable in principle, and thus they're just not a scientific concept. Hossenfelder, our favorite one to pick on, this is what she says, by definition, if we're trying to determine whether these infinities exist, we're never going to be able to tell, because that's the definition of infinity. No matter how big you measure, it's always going to be one more. But of course, not all singularities involve infinite quantities. The curvature ones do, it seems like. So what about those? I have a long quote, I won't read it all, but basically this is from Ehrman. He's saying, okay, how could we tell? You're falling into the black hole, you're carrying your ruler and your measuring instrument. How can we tell the difference between a case where your geodesic is in principle inextendable beyond a finite proper time because it encounters unbounded curvature, compared to a case where your world line is extendable in principle but not in practice because your measuring instrument is getting crushed, right? You will never be able to tell the difference here. Still, he's saying, yeah, we can't tell the difference, but again, I think this kind of line of reasoning I was just saying, we have reasons to trust GR, why not take this also as a prediction? Okay, so another reason, that's the prediction or tolerance for singularities. Another reason why we might not want to get rid of singularities in our theories is this emergent physics view. If you've read Batterman, he's arguing that for our theories to give us emergent quantities, we need to appeal to these kind of limiting infinite limits. And we can't describe the emergent behavior we want if we have a finite theory. So then we need them for adequate description of our low energy physics. So we keep them in. And the third one, which is quite interesting, as I said, we found these by just scanning the literature. This is an argument from Horowitz and Myers saying that we need the singularities in order to have a stable ground state. But I'll leave you to have a look of the details of this one. So those are 3 examples of attitude 3. And finally, attitude 4 is indifference to singularities. So instead of having this positive attitude towards them, which was attitude 3, you're just saying, meh, I don't care. They're there, whatever. It doesn't make a difference because although our theories have these problems, we're looking for a new theory anyway. We're not treating these as fundamental, but the singularities aren't telling us anything. So I think, when talking about QFT, Wallace is arguing that if we're treating our quantum field theories as effective theories, then, okay, it means that we're not expecting them to be fundamental. So even if they're featuring singularities, that doesn't matter. Or this asymptotic safety view, where you're just thinking, well, okay, yeah, the singularities appear, but it's just an effective theory. We're not worried about it. And Eric, this argument that I mentioned at the very start of this talk, well, it's not a problem for GR because they're not kind of living in space-time. There we go. And this Brandenburger and Waffer, who are arguing from string theory, that, okay, even if there is this singularity, the strings don't see it, so it doesn't make a difference. Okay, and they're using, is that my signal time is up? Arguing from T-duality there. So, yeah, that's the summary. I would say by themselves, they're not automatically pointing to new physics, but, maybe they can give us interesting motivations, depending on how you want to resolve them. But it's going to depend on your attitudes towards these internal versus external motivations. Whether the singularities need to be resolved within your theory, or you have reasons for thinking that this theory is not fundamental anyway, and it will be resolved there. So, yeah, thanks.